Today let us look into design of the phases one by one. Let's start with the first phase, that is the simplest phase, lexical analyzer. What is the main function of a lexical analyzer? The main function of a lexical analyzer is read the source program line by line, read every line character by character and divide that into group of characters called tokens. No doubt that is the main function of any lexical analyzer. In addition to this main function, a lexical analyzer even performs other tasks. The other task performed by lexical analyzer is it removes comment lines and white space characters correlating the error messages. Let's see what does it mean. White space characters and comment lines actually are not required during the translation from source text to assembly language. Hence, lexical analyzer just takes out all that comment lines and white space characters, which also no white space characters means new line, tab, space, all that, which is not required during the translation. So that is what this means. And what about correlating the error messages? We already discussed how exactly error handler is used by every phase. Errors are most common in every phase. So in order to deal with that errors, every phase will have error handler. So whenever any phase encounters a error, for example, a syntax analyzer encounters an error that plus is missing, semicolon is missing. If it simply gives an error message like plus is missing or semicolon is missing, is it understandable? Generally, the error diagnostic should be something like in so and so line, so and so is missing, isn't it? So it needs a line number with which actually it has to give the error message. Out of all the phases, since lexical analyzer is the only phase which reads input stream character by character, it while reading the line number, it actually remembers the line number of the code, such that whenever there is a error in any phase, it actually helps the other phase in giving the error diagnostic along with the line number. That is what we mean by correlating the error message. A lexical analyzer keeps track of line number of every line in the source code. As and when there is an error captured by any of the phase, to help the phase to give the error diagnostic along with the line number, the lexical analyzer actually helps. Now, one more question. Why to have, see, the task is very simple. Lexical analysis task is read and give stream of tokens. Why to have this as a separate phase? Can't we have it combined with the other phases or something like syntax analyzer or semantic analyzer, something like that? There are advantages of having this lexical analyzer as a separate phase. The advantages are the design is simplified, portability is enhanced, and efficiency is improved. Let's understand what do we mean by all this. Design is simplified. Naturally, instead of having a complex module as one single task, when you subdivide into different modules, sub-modules, naturally the design is simplified. So naturally when you have it as a separate phase, design is simplified instead of having that along with other phase. What about portability? Remember, lexical analyzer phase actually takes care of the input peculiarities of any high level language. What are the keywords supported, what are the operators supported, and what are the different symbols supported. All that input language peculiarities are handled at the lexical analyzer level. So while writing the code for this, if you take care of how well you can enhance this or port this for some other language, easily portability also can be enhanced. And coming to the compiler efficiency, which way having this uh, lexical analysis as a separate phase improves the efficiency of the compiler. Means while writing this particular module, if this particular module is implemented in an efficient manner, naturally, since it is part of the compiler, that contributes to the overall efficiency of the compiler. And remember, out of all the phases, compiler spends much time in reading each character by character only in lexical analysis phase. That's why it spends much time in lexical analysis. That is the reason, if this phase is implemented efficiently, that contributes to the overall efficiency of the compiler. Now, let us see how to implement this. Generally, lexical analyzer is implemented as a subroutine. How exactly it works means, a lexical analyzer will not read the complete source text at once and gives all the stream of tokens at once. Actually, it works as an interface with the parser, that is syntax analyzer. So, it is implemented as a subroutine. During parsing, during the syntax analysis, whenever parser requires a token, actually it makes a call to the lexical analyzer, something like get token. On getting the request from the parser, the lexical analyzer reads the next token and sends the next token. So, that is communicated to the parser through some function, something like send token. If at all that token happens to be an identifier, it even stores that into the symbol table. That's how the interaction between lexical analyzer and parser can be depicted like this. It is implemented as a subroutine. As and when it gets a request from the parser, reads the next token from the source code and sends that token to the parser. If it happens to be an identifier, stores that into the symbol table. So, in lexical analysis, we use the terms like token, lexeme and pattern. Let's try to understand what does it mean. Let me take an example. Lexeme, pattern and token. These are the three important terms. Actually, pattern is nothing but the rule, the lexical rule. The rule with which, by using which, you can group stream of characters into tokens. Lexeme is nothing but the actual character stream that represents the token. And tokens are nothing but logical sequence of characters with some collective meaning. For example, in a high level language, all the keywords are taken as separate tokens, all the identifiers are taken as separate tokens, all the operators are treated as separate tokens, all the punctuation symbols are taken as separate tokens, and all the numerical constants are taken as separate tokens. Let me take an example. Suppose I have a statement something like constant pi is equals to 3.14. This is my statement. Let's try to understand what do we mean by lexeme, pattern and token here. If you look at the first word, constant. Constant here is what? It is a keyword, a reserved word, isn't it? So, the rule for identifying the, suppose if we assume that our lexical analyzer takes every keyword as it is as a token, every operator also as it is as a token, and every identifier, representative token is something like ID, and for every numerical constant, representative token is something like num. If we assume, see, before writing any lexical analyzer, we need to be very clear about what are the tokens you are assuming in your particular language. So, here I am taking keywords as separate tokens, operators as it is as a token, and punctuation symbols also as it is as a token, and numerical constant representative ID is num, and for identifiers representative token is ID. Okay. So, here constant is, what is the rule to identify this keywords? Keywords are all reserved. So, that sequence of characters representing the keyword itself is a rule. So, here whenever you get CONST, if this is the pattern, then the token is also same, and here the lexeme, actual character stream, is also same. For keywords, all the three will be same. And coming to the next one, pi. Pi is what? Actual character stream is pi, When you read pi, pi comes under which category? It is a keyword. How do you say keyword? How do we recognize any keyword in any high level language? The generally lexical rule for identifying any keyword is every keyword always starts with a letter followed by any number of letters or digit. So if I use regular expression, I will say the rule is letter followed by letter or digit star, any number of letters or digit. This is the lexical rule or pattern using which I can take the input string and group that into the token ID. Now next is equal to. Since every operator is taken as it is, so token is equal to. Then for 3.14, any numerical constant, any numerical number is taken as a ID now. Then comes the punctuation symbol. It comes under punctuation symbol and token here is as it is semicolon. So this is how we actually use patterns to group the lexemes into corresponding tokens. Okay. Now let us see how to design the lexical analyzer. Let us see how to design the lexical analyzer. There are two ways of designing the lexical analyzer. One is you can use lexical or you can write your own hand coded lexical analyzer. Use lexical or write your own hand code. So whether you use lexicode or you write your own hand coded lexical analyzer, the main steps to be followed is actually once again two steps. First step is, in order to, task is what, given a text, source text, we need to identify tokens out of it. How do you identify tokens out of it? For that, first you need to have the lexical rules. What is the rules with which you can break the source text into tokens? So the first step is define lexical rules. We say otherwise pattern using regular expressions. Like just now I said, example, identifier can be letter followed by letter or digit star. So first define, if it is an identifier, what is a rule? If it is a keyword, what is the rule with which I can identify a identifier or a numerical constant or an operator? So once you have good knowledge about all the rules, then to make it more automative, or what we can do is convert this regular expression to finite automata. So once you convert these regular expressions to a finite automata, what is a finite automata? It's a mathematical model. Given any string, it always says whether the string is accepted or rejected. So once you have this mathematical model, given any string, if it is accepted means it is a valid token. If it is not accepted means invalid token. That is how we validate the tokens. So to convert regular expression to finite automata, generally what is that we do? We convert, there is a mechanical procedure of converting a given regular expression into NFA with epsilon moves, which is called Thompson construction. Then once you have NFA, you can straight away convert this into DFA. So convert that into NFA, NFA to DFA using subset construction. So if you use a lex tool, actually this part is automatically done by the tool itself. Given input for a lex tool is only regular expressions for every token. So given that as a input, it automatically builds its own table driven finite automata, using which you can always check out which is a token, which is not a token. Even when you write your hand coded also, you can follow the same steps. So regarding regular expressions, finite automata, conversion of NFA with epsilon to without epsilon, or NFA to DFA. All this you might have studied in your automata theory and formal languages or theory of computation. So I will not be going more about this. In lexical analyzer, generally we can expect questions something on given any source code segment. You may be asked like checking out the number of tokens out of it. Let's see few examples. Let us try to understand, given a segment of code, how exactly the lexical analyzer gives stream of tokens. Let us take these two examples. Given this segment of code, let us see how to get the number of tokens out of it. For example, if you take the first one, how many tokens we get out of it? Here, float is a keyword, one token. Fun is a function name, another token. Left parenthesis, another token. Keyword, operator, identifier, operator. Then curly braces, another token. Keyword, another token. Left parenthesis, not equal to another token. String compare, keyword. Left parenthesis, identifier, operator. Literal string, whatever you have within double quotes is a literal, will be treated as a single token. Closed parenthesis, another closed parenthesis. Written is one token. 0 is another token. Punctuation symbol is another token, and closing parenthesis is another token. So let's count how many we get. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This complete thing is 1, 16, 17, 18, 19, 20, 21, 22. So 22 tokens. So here you may wonder what to do with this. We already discussed lexical analyzer eliminates or removes all the comment lines. So no need to consider comment lines. Comment lines is not a token because it is before starting the lexical analysis phase. It actually, first step is removing all the comment lines. Let us look at the second example. In fact, this was asked in 2000 GATE paper. Find the number of tokens. It's something like A is 3, B is some 26, C is 10 and D is none. Which is the right answer? Now check out the number of tokens out of this code segment. Same as the first example. So what is the answer? Let us see. This is one token, printf, 2. So the main confusion would be mainly on this literal. Remember, whatever you get within the double quotes is treated as a single literal. Compiler need not have to analyze what is there inside the literal. It is only the IO routine that has to analyze what is there inside this double quotes. So this complete thing is treated as a single token by the lexical analyzer. This is another, this is another token, this is the next token, another token, next token, another token. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hence C is the right answer. This is how we check out the number of tokens out of the given code segment. Let's look at these questions, previous GATE questions. For example, if you look at this, match the following based on the input. So if you look at syntax tree is input for what? Is it an input for code generator? No, because for code generator means target code generator, input is either from the code optimizer or intermediate code generator. Or syntax analyzer produces syntax tree, so it cannot be input for syntax analyzer. So the best part would be syntax tree can be input for semantic analyzer. Okay. Now coming to character stream. Character stream means source text. Source text can be input for what? To the first phase, nothing but lexical analyzer. And coming to intermediate code generator, actually gives input for target code generator. If you take out the optimization, whatever the intermediate code produces, the 3 address code, from there actually target code is generated. R. And then token stream is the output of lexical analyzer, and that will be sent to syntax analyzer. So token stream will be input for syntax analyzer. So we have seen the phases of compiler. From that we can actually match all this based on input. The other one is this one. This was asked in 2016. Match lexical analyzer, top-down parser, semantic analyzer, runtime environment with leftmost derivation, type checking, regular expression and activation records. So lexical analyzer actually uses regular expressions for defining the in the design of lexical analyzer. We use the regular expression, so you can match this with this. And top-down parsing, so parser actually uses this leftmost derivation for parsing the given input stream. So here this is the key. And semantic analyzer performs what? Type checking. And left out is runtime environment. Runtime environment actually, in order to execute any program or a function, the information required for the execution of any function is stored in a record called activation record. So during the execution, that is at runtime, it actually stores that information in the activation record. So you can match runtime with activation record. So that's all regarding the lexical analyzer. Now let's go to the next phase. What is the next phase? Syntax analysis. So syntax analyzer main function is what? Given a source text, it has to verify whether the syntax of the given statement is right or wrong. So for that, how exactly a syntax analyzer or a parser works? It takes the given source text as something like input string. In order to verify the syntax of this input string, it uses the standard syntax which is defined by the grammar, context-free grammar. So uses the grammar. With the help of the grammar, it verifies whether the given input string syntax is right or wrong. How exactly it verifies? The task is something like, given an input string for which you have to verify the syntax and a grammar in hand. The task is now something like, given an input string and a grammar, verify whether the input string is derivable from the grammar or not. If at all the input string is derivable from the grammar, syntax is right, else the syntax is wrong. So remember, in the design of a parser or a syntax analyzer, grammar plays a major role. So before going to the design of parsers, let us spend some time in understanding few concepts of grammar which are mainly useful for design of the parser. So let us look into grammars now.